this absolute Galois group of the p-adic numbers using our bare, using what I want to argue is low-level methods. I mean, they look pretty fancy because I've used things like the fundamental theorem of Galois theory for infinite extensions or whatever. But in some sense, this is hands-on methods that you can really, as a first-year graduate student, say, you can somehow really go away and read all the details. But I now want to talk about class fill theory. So I'm going to state the results. And this is somehow, I always feel that this is genuinely harder. Although, of course, we now have very nice write-ups of it. And one really could go away and read the details. On the other hand, somehow filling in the gaps in these lectures here is not really a challenging task, whereas reading the proofs of the theorems of local class fill theory is definitely possible, but it will take you a while. I mean, somehow there are clever tricks involving loop intake groups, but they're not the kind of things you could generate yourself. You need to have had a genius going before you to understand class fill theory. Right. So here we are then, local class fill theory. So we've just seen that an attempt to analyze the group gal k bar over k via some kind of explicit attack on the inertia group, right? On the inertia group. Because somehow what I've basically done is I've shown that you have the full Galois group, and then you have the inertia group, and the quotient isn't too bad. Then the inertia group, there's a normal Suloff P subgroup, and the quotient isn't too bad. And then the Suloff P subgroup, these low-level methods kind of don't get you any further. The inertia, so the obstacle you run into is that the Suloff P subgroup of the inertia group is hard, right? I think there are people that somehow claim to be able to write down generators and relations for this thing, but I've never looked at the details. So here's another approach. So here's another. Here's another approach, and what I'm going to do is I'm going to try and understand the abelianization of this thing here. Let's understand. Try and understand the abelianization. So this is different, right? Somehow, we've got the inertia group and wild inertia group. These are random subgroups, but now we're doing something else. Now we're just quotienting out by some commutator subgroup. The abelianization of this Galois group. And here, I can't give proofs, so I'm going to just have to give statements. So the statements come out nicest if I use something called a Weil group first. So let me give the following definition first. So here's a key definition, the Weil group. So let's have K over QP finite. So recall, that we have some exact sequence. So the trivial group goes to I k bar over k, goes to gal k bar over k, and then this goes to the absolute Galois group of the residue field, goes to z hat, goes to 1 there. So this is generated by Frob. Some element called Frob, which, as I say, is this is not right. This is KNR. Sorry, I've made a typo. KNR over K. This is generated by Frob. Frob is not really an element of gal k bar over k. Nothing's right. Sorry, this is fine. This is gal. Sorry, I hadn't made a typo. Frob is really an element of this z hat. You can lift it to an element of gal k bar over k, but of course there's lots of lifts, and any two lifts will differ by inertia. So Frob is not really a well-defined element of gal k bar over k, but it's a well-defined canonical generator of this z hat. And what I want to do, for reasons which somehow initially I found very bizarre, is I want to change this z hat to a z. Okay. So I want to look at I want to, let's look at Frob there. So Frob is in z hat, and so let's look at Frob to the power z, as it were. So this is whatever the identity. Well, it's ... Frob inverse, Frob to the -2, Frob to the -1, the identity Frob squared. There. That's a group which is canonically isomorphic to Z, right? And that lives in Z hat. And for some reason, I like the inertia group, and I'm going to leave that alone, but I don't like the Z hat. I would rather have a Z. And so let's give us a Z. So let's define the Weil group. The Weil group WK of K by the following picture. So this is a definition of the Weil group as a group. So here's the identity, and here's the identity, and here's the inertia group, and here's the inertia group, and that's an equality. And here is my Weil group, and here is my Galois group. And the Weil group is going to be a subgroup of this. And what's happening is if I quotient out the Galois group by the inertia group, I get a Z hat. And now I've got this Frob to the power Z. This is a group isomorphic to Z, and that lives in there. And I'm going to put 1 here. And now I can kind of glue everything together there. So that's a rather informal definition. So if you like, formally, WK is the G in gal k bar over K, such that the image of G in Z hat, which is gal K and R over K, is actually Frobenius to the power Z, right? If you like, you can just call it Z. If you're happy about, Z living in Z hat. So that's what the Weil group is. So it certainly contains all the inertia group, because the image of something in the inertia group in this is 0. And then we have all these. It's difficult to know, when you have long exact sequences of groups, some of which aren't commutative, it's difficult to know whether 1 is supposed to represent the trivial group or 0. I mean, if you want this to be a 0, I don't know. This is the group Z hat under addition, and this is the identity. This is the group with 1 element under multiplication. So it's slightly messy. So there's a rather strange definition of a Weil group. So the Weil group is somehow a dense subgroup of the Galois group. I want to give it a topology, but the topology is not the subspace topology. So this is a slightly delicate point that in some sense we were talking about yesterday afternoon. The way this is going to work, so let's topologize WK. Thus, I want this inertia group, I want IK bar over K is going to be open, right? With the usual topology. So IK over K is not an open subgroup of gal K bar over K, right? In fact, IK over K is a closed subgroup of gal K bar over K. Z hat is a, Z hat looks a bit like the p-adic numbers, right? The ZP, that's not a discrete group. The identity, 0 in ZP, that's a closed subgroup, but it's certainly not open. So the kernel of this map is the preimage of the identity here, so it's the preimage of a closed set, so it's closed. The inertia subgroup is closed in gal K bar over K, but it's not open in general. So I'm going to make the inertia subgroup open in WK with the usual topology. And so that means, so WK modulo IK bar over K is Z. And what's the topology on this? This will be with the discrete topology, right? With the discrete topology. So in particular, this was something that confused me at the time when I was learning this stuff. In particular, WK does not have the subspace topology. It is a subgroup of this Galois group, but it doesn't have the subspace topology. Right? So if you want to be a real pro, then here's a way of thinking about WK. You could have Z with the discrete topology, and that maps down to Z hat with the usual pro-finite topology. This is a projective limit of Z mod NZs. So it gets this pro-finite topology. So you think about it, this map is a continuous map. Why is it continuous? It's because the source has the discrete topology, so every set is open. So the preimage of an open set is open because the preimage of an open set is a set. So this is definitely continuous. And then I have this group, this here, gal K bar over K. And that's continuous as well. And WK is the pullback in the category of topological groups. There. In the category of topological groups. So I don't know if that helps, but it's just, that's what's going on. So I'm doing two things. I'm replacing the Z hat by a Z, but I'm also changing the topology. I'm putting in more open sets. So there's the Weil group. And one wonders why it's there, at least at this point. And the reason it's there is because I want to understand. You see, the Weil group, we haven't lost much, right? The Weil group is a group, it maps, there's a continuous map into the Galois group. The image is dense, so we haven't lost much. And also, somehow, if you imagined a finite extension, L over K, and you somehow imagine the image of the Weil group in the Galois group of a finite extension, that's going to be surjective. Because Z injects into Z hat, and it's certainly not surjective in general. Z hat is uncountable, right? So this is a tiny subspace of Z hat in some sense. But if I look at some finite quotient of everything, then Z hat becomes z hat mod n z hat, which is just z mod n z. And z goes to z mod n z is surjective. So the V group doesn't map surjectively onto this Galois group, but if I replace k bar with any finite subset, with any finite Galois extension, the V group would surject onto it. So we haven't lost much information in some sense. We've just, I don't know. So it turns out that local class field theory tells us what. So maybe I should just say, what's an abelianization here? Let me define for G, a topological group, topological group. Let's define the subgroup. Let me call it GC to be the topological closure of the subgroup of G generated by commutators, of the subgroup of G generated by the usual thing is kind of G, H, G inverse, H inverse for G and H in G. So see, if you just had an abstract group and you wanted to look at abelian quotients, you would look at the subgroup generated. I mean, I suppose I could put the normal subgroup. Turns out these are the same thing, but let me. You don't have to worry about that. Let's look at the normal subgroup generated by these things here. The idea is that normal subgroup. If I quotient G out by this abstract normal subgroup, I'll get a group which is abelian because I've thrown in all the commutators. But if G is a topological group and I just generate this random subgroup here, then this random subgroup, if it's not closed, then when I quotient out G by this closed subgroup, by this random commutator subgroup, I'll just get something that's kind of horrible. I'll get something that isn't Hausdorff. So the idea is that G mod then G modulo GC is the maximal abelian Hausdorff quotient of G. So GC plays the role of the commutator subgroup of G in this situation where we have a topology there. So I want to call this G ab there. I don't really want to be bothered with non-Hausdorff topological groups. Maybe I should just. This theory of topological groups is somehow something that passed me by. There was a course on topological groups available to undergraduates somehow 2 years before I got to it, but it was like everyone found it very difficult, so the course was removed. But basically the one thing you need to know about topological groups is that if the one weird thing about non-Hausdorff topological groups is if you really have a group with a topology and the identity is not closed, then the closure of the identity, that's a subgroup, and that subgroup is somehow a basic unit as part of the topology goes. Like, that's a closed set, and all the kind of cosets of that are closed sets. And and this subgroup is normal, and you quotient out by that closure of the identity, and then you get a Hausdorff group. Now points are closed, and life is good. So this is sort of weird. That's what I'm doing, really. This, first of all, I'm quotienting out by the commutator, and then I'm taking the closure of the identity because I want points to be closed. So there's how I do abelianizations of topological groups without ending up with weird non-Hausdorff groups. And really, I'd like to tell you about the abelianization of the absolute Galois group of K. And I know what that abelianization is, but it's a little bit weird to write down. And it turns out if you do this, one of the nice reasons about working with the V group and not the Galois group is the abelianization of the V group comes out to be really, really nice. Right? So that's the big theorem. So here's the theorem. So my main theorem of local class field theory is the abelianization of the Weil group. So K over QP finite. Then there's a canonical map isomorphism, the Artin map, RK, and it goes from K star to the abelianization of the Weil group. There. I'm going to write more things about this, but let me just remark before I go on. When I was your age, I was still a little bit freaked out by this weird definition of the Weil group, because it's not a profinite group. We've got this profinite inertia group, and then we've got this random discrete part. And it seemed a little bit weird to have some kind of a group that had a profinite bit and then a discrete bit. I mean, what kind of category was this group supposed to live in? But when you think about it, that's exactly what K star looks like, right? K star has got OK star, the integers, or the units, which are a profinite group, and then the quotient K star by OK star is just a copy of Z, the integers, with the discrete topology. So in fact, K star has a very similar feeling to WK, has a profinite part and a discrete part, and in fact, it turns out they're related. There's a canonical isomorphism RK from K star to WK have. And I need to tell you some properties of this canonical isomorphism, and they're not exercises, because to do the exercises, you'd have to know where the definition was. So I'm not going to tell you where the definition comes from, but it's hard work, right? There's a canonical isomorphism from the abelianization of this Weil group to K star. Let me list. Here's a list of properties. Here's a big list of properties. Of this isomorphism. Well, we kind of have filtrations, right? We have filtrations on this Galois group, so we get filtrations on the Weil group. And I'm going to put filtrations on K star, and the filtrations are all going to match up nicely. So local class field theory is great because you don't actually have to go away and read the proofs now. If you just know this list of properties, then you know enough to use local class field theory in practice. So if you want to see why this is true, go and read, I guess it's Serre's article. Yeah, go and read Serre's article in Cassel's Froelich, where all the proofs are beautifully presented. There's lots of different proofs, actually. So let me tell you some stuff then. So we've got RK. This goes from K star to the abelianization WK. And K star contains OK star, right? The integers. And now if you think about it, this is profinite, and then the quotient is discrete. It looks like Z. So where do you think this is going to go? This is going to go to the image of I K bar over K. Right? That's the inertia subgroup. And in fact, that's, well, remember WK, this is a quotient of WK, right? So we can look at the image of IK over K. And now this contains 1 plus pk to the power I. So for I is at least 1, we have this filtration on the units. We have the 1 units, and then we have the things coming to the identity modulo higher and higher powers of this maximal ideal. And of course, so these match up. So what does this match up with? This matches up with the image of I K bar over K. This is going to be one of these numberings, right? This is either going to be the upper numbering. This I haven't finished yet. I need to put an I somewhere. And it's either going to be the upper numbering or the lower numbering, but it can't be the lower numbering because I'm working with infinite extensions here. So the upper numbering is the only thing that makes sense. So it's going to have to be the upper numbering. And that's a bit weird because normally the upper numbering kind of jumps around loads, right, at random rational numbers, whereas this filtration only jumps at integers. But remember, the Hasse-Raff theorem says that in the abelian situation, all the jumps, even for the upper numbering, are integers. So this is not surprising if you know about Hasse-Raff. So that's kind of cool. And now I should probably say that K contains pi k, right? Rk and Rk of pi k. Pi k is some random element of K. There's no canonical. This is kind of interesting, right? This is K star is this local field, and the units in this local field are a completely canonical thing, but the uniformizer is not canonical. You have to choose a uniformizer. Like if K is QP, typically everyone chooses P. That's sort of a sensible uniform. But for a random finite extension of QP, you've got some Eisenstein polynomial, and the roots of this are all uniformizers, and you can't distinguish between them from some conceptual manner. So this isn't really a well-defined, pi k is not a well-defined thing. There's some ambiguity in the choice here. So there should be some ambiguity in Rk of pi k. And Rk of pi k lives in, let's say, Frob, well, inverse, let's say, times I k bar over k, the image of I k bar over k. Where's my Weil group? Have I lost my Weil group? Yeah, I've lost my Weil group. Remember we had I k bar over k, and that went to wk, and that went to z, right? And we have a 1 here, and that goes to, we can lift that to a Frob here, and that Frob is not well defined, right? But the coset of inertia in Frob, the coset is well defined. So I'm making an assertion about something landing in a coset. So this is a very strange theorem because WK is somehow about some external, this is about things, we have K and then we have kind of K bar, and the Galois group of this is essentially WK. So this is about some kind of external properties of K, things about K bar. This WK is defined using objects which are much bigger than K, whereas this K star is somehow defined only using K itself, and the structure we're putting on K star all comes from kind of subsets of K that depend only on K. So this is a very remarkable theorem in some sense, because it says some kind of external structure attached to K is very closely related to some kind of internal structure. Some funny thing. So there's this amazing map Rk, and I'm not going to tell you where it comes from. But I am going to make a confusing remark. So before I write down some more properties of Ik, let me make some confusing remark. I really like the idea of things being canonically isomorphic, and one of the reasons I like it is because it's very difficult to write down a definition of canonically isomorphic. So I asked Gordon James once, an algebraist in my department several years ago, and he said that Conway had once told him that the definition of canonically isomorphic meant that these were isomorphic, and if you asked your roommate to write down an isomorphism, and then you wrote down an isomorphism, then you would write down the same isomorphism. And I thought that was kind of a nice definition. And I think in many cases that does work quite well. But here's a weird thing, right? I don't really know what canonically isomorphic means, but if X and Y are two abelian groups, and they're canonically isomorphic, and if phi from X to Y is a canonical isomorphism, then I can think of another canonical isomorphism, because this is an abelian group, and so it comes with a canonical involution, right? Then psi from X to Y defined by psi of x is is kind of phi of x inverse. That's also an isomorphism. And in some sense, it's just as canonical. Is just as canonical. That's phi. So when I was a graduate student, I had to read this book by Katz and Mazur. And the first time I saw it was in the Weil pairing, right? There's some Weil pairing. If E is an elliptic curve, E is some elliptic curve, then there's some pairing on En cross En to mu n. It's the Weil pairing. And in Katz and Mazur, they say we should explain how to normalize the Weil pairing. And I kind of thought, this is ridiculous. In this day and age, surely there's nowadays some kind of canonical normalization of the Weil pairing. But in fact, the problem is the Weil pairing is canonical. And so we run into exactly this issue, because all these groups are abelian. You can write down a pairing, and then somebody else can just decide that they want to apply the inversion map on mu n first. And then they've got another pairing, and all the theorems which are true for one are true for another. Okay, the only difference is when you start explicitly writing down examples, then you get kind of the inverse dual roommate. So this is a problem that's never going to go away. I've claimed that we've got two groups here which are canonically isomorphic, and I said that RK is a canonical isomorphism between them. But the problem is, if I do RK follow, like K star has got this reciprocal map, if I do the reciprocal map and then RK, we get another equally canonical isomorphism. If you think about it, all of these things about, you see the inverse of OK is going to be OK, so if that's true if I change RK to its inverse, then this will still be true, and this will still be true, because the reciprocal of this is this. But this is the thing that isn't true. This is the thing that tells us which one it is, you see. Because if I change RK of pi, if pi k is a uniformizer, the reciprocal of pi k is not a uniformizer. So what's actually going on, philosophically, is that there's two canonical isomorphisms between K star and WK ab. And they're both canonical, and you can tell the difference between them. That's the point. Because one of them sends a Frobenius, one of them sends Frobenius to a uniformizer, and the other one sends the inverse of Frobenius to a uniformizer, right? So there's two ways to normalize class field theory, and the reason that there's two ways to normalize class field theory is that every abelian group has a canonical automorphism, which is inversion, which is never going to go away, you see. So in fact, there are always, so there are going to be two ways. There are, in fact, two canonical isomorphisms between K star and WK ab, right? Namely, RK and RK inverse. Okay, and these first properties here, and I'm going to write down loads of other properties of RK in a minute, but I've started waffling on about this when I've stopped waffling on about this confusing remark. And all the other properties I write down, you will be able to observe that if you all looked away and I replaced RK by its inverse, then all the properties I'm about to write down still would remain true. But this is the only one that actually tells you which one I'm talking about. Okay, there are two canonical isomorphisms, namely RK and RK composed with x goes to x inverse, right? So the way you tell between them is you say what happens to a uniformizer and a Frobenius, right? So we can tell them apart by this last condition here, right? The one we will use identifies a uniformizer pi k in K star with the inverse of Frob Q. Right? And the other one doesn't. Okay? So Deligne, so the question is, which one do you use, right? They're both absolutely fine, and all the theorems will be fine for everything. But the problem is, if half the people in the mathematical literature use one, and the other half use the other, then it gets difficult when you're, I mean, I've had personal experience of this. You're trying to quote results from random papers, and they say by class field theory, you see this is true, and they write down some statement, and it turns out the statement they write down depends on whether they've chosen RK or the inverse of RK. And so then you have to look in the paper and see if they've explicitly said what their normalizations for local class field theory are. And some people say, and some people don't say, but Deligne somehow thought very hard about it and decided that this was the best one. So this is the one I'm going to use. So Deligne, definition geometric Frobenius. It's the reciprocal of Frobenius, right? An arithmetic Frobenius. Is Frob. Right? Frob is the one that Frobenius knew something about. And Frob, you see, this is the problem. Frob is the thing that every single person pre-1970 called Frobenius, right? That was the Frobenius. It was x goes to x to the q. That's what people talked about. And then somehow when people were doing calculations in étale cohomology, it turned out that the interesting thing was Frob inverse. Frob inverse was the thing because somehow it was cohomology, not homology. The inverse of this usual Frob was the thing that kind of had all the interesting eigenvalues and everything was kind of normalized, right? So Deligne wanted a word for it, so he called it geometric Frobenius. So then all of a sudden, Frob inverse was a Frobenius as well. So now uniformizers get identified with Frobeniuses, and all of a sudden we've kind of lost track of which one we're using. So you will see in well-written papers, you will often see remarks to the form, we normalize the isomorphisms of local class field theory so that a uniformizer becomes identified with a geometric Frobenius, right? Do what Deligne does, right? Do as Deligne. Okay, uniformizer is related to geometric Frobenius. Okay? Because if we all do the same, then we won't have to deal with the nightmare that basically I've had to deal with in the past, ploughing through papers and trying to figure out how their normalizations are. Right, so anyway, there's a 15 minutes of waffle now saves years of pain later. How are we doing? I've got no idea. We stop at 12:15, right? I'll try and stop on time this time because food's involved. Right, so I'm stating the isomorphisms of local class theory. I've told you, so here are some, so I need to tell you more properties of RK. So I've nailed down which one of these two canonical isomorphisms I'm using, and I've remarked that you can never get away with the fact that there are two canonical isomorphisms. But I've hopefully made it quite clear which one I'm going to be using myself. So more properties of RK then. More properties of RK. Of course, if L over K is finite, then we have some kind of commutative diagram, right? Then of course, gal K bar over L, that will be a subgroup of gal K bar over K. And so one can check that, in fact, the Weil group of L, which lives in gal K bar over L, then gets identified with a subgroup of the Weil group of K. So in particular, there's a canonical map from the Weil group of L to the Weil group of K. And now this AB business, which is take the maximal Hausdorff-Abelian quotient, that's of course a functor. So if I take the maximal Hausdorff-Abelian quotient of WK, I get WK AB. And the map from WL to WK AB will end up, the image of WL will be Hausdorff and abelian, so it will factor through this, right? WL ab. There's going to be a map from WL ab to WK ab. And this map from WL to WK is an injection. That's just kind of the fundamental theorem of Galois theory, right? I replace K by a slightly bigger field, I get a smaller Galois group. But when you abelianize everything, that injectivity is lost, if you think about it. Right? For example, if this is some crazy, complicated, finite, simple group, and this is just a random cyclic subgroup, take a random non-trivial element and look at the group it generates. I'm going to map from a cyclic group into a crazy, simple group, which is an injection. When I abelianize, the simple group becomes trivial, but the cyclic group still remains cyclic. So you see an injection can become a surjection. You've got to be a little bit careful here. So this map, I mentioned this because this confused the hell out of me for about an afternoon. When I was trying to understand this stuff. That map from WL ab to WK ab might not be an injection anymore. But we've got a commutative diagram going here, right? So what's happening here? I've got RL. So we have L star, and now we have RL, canonical isomorphism to WL ab. And now I've just shown that there's a natural map down here to WK ab that when I was your age I was pretty convinced was going to be an injection because I wasn't thinking straight. But now I've realized it's not an injection at all. Which is kind of good because there's L star and here's K star. And there's my isomorphism here, RK. And if I had to come up with an injection from L star to K star, that might be quite difficult because L star is much bigger than K star. So there's going to be a map there that this was a completely kind of canonical natural map. So I really kind of wanted the answer to be, well, there's a completely natural inclusion from K into L, but that goes the wrong way. So it's slightly, there's supposed to be a map from L star to K star, which, as I say, in my head at the time I thought was going to be an injection. So I was a bit muddled about what this map should be. What do you think this map is? Yeah, it has to be the norm, because it has to be a group homomorphism, right? And yeah, this is going to be the norm from L over K. It's just the only possibility. And it turns out so that diagram commutes. There. Which is a bit funny because, as I say, the natural map is from K star to L star. So there's going to be some other commutative diagram that goes, there's surely a map, I've got an inclusion from K star to L star. And that has to correspond to some map here, which is a map from the abelianization of a group to the abelianization of a subgroup, which is a bit funny because normally you don't see maps from, like, there's a natural inclusion from the subgroup to the group, but how the heck are you going to get a map from the group to the subgroup? But in fact, it turns out that in group theory there's a norm as well, right? WL is a finite index subgroup of WK, right? L over K is a finite extension, so WL is a finite index subgroup of WK. So I'm going to give you a map from WK to WL, kind of take an element of WK, and then kind of, there's finitely many cosets, and each of those, we could take a set of representatives of the cosets, and then we could take, I want to do norm, right? I'm trying to define norm from WK down to WL. So WK is a finite union of cosets of WL. I could take a set of representatives. Then given an element here, I could take the conjugate by all the sets of representatives and multiply them all together, and that would maybe give me an element of WL. But like, these groups aren't commutative, so that would kind of be hopeless. So somehow trying to define a norm in this generality is a complete fail. But actually, if you abelianize everything, everything works, right? So there's some weird Verlagerung map, right? This is this is what we call the transfer map. So if the situation is if I've got H lives in G, this is finite index, right? Then there exists some V from G ab to H ab, right? Which is just an analog of the norm, you see. And so that Verlagerung, we'll never use this, I'm just kind of telling you. I'm just basically listing all the properties of class field theory I can think of. So it's basically G goes to kind of the product for I is 1 up to n of gamma I G gamma I inverse, where kind of gamma I set of coset representatives. And this is, you never do products like this in group theory because that's, you have to say what order we're doing everything in and blah, blah, blah. But in Abelianization, it works. So here's the next property of a. Next property of these RK maps is that we have L star, K star, and we now have the inclusion, and here's RK, and here's WK ab, and here's WL ab, and then this thing here is this transfer map. There. RL. And again, you see, you can't, this isn't an exercise because you don't know the definition of RK. But basically, what I'm trying to do here is I'm trying to list enough properties of local class field theory that will last you a lifetime. And I think I might have done it. Yeah. Let me just make one more remark. If you ever actually need to get your hands dirty and really know something about what does class field theory really do? Local class field theory offers you several things. Local class field theory offers you an interpretation of the abelianization of this Weil group, and hence an interpretation of the abelianization of the Galois group, really, of K. So it offers you this, but it actually, when you look at the proofs, it also, or you look at the modern proofs, by which I mean the proofs from the 60s, as opposed to the original proofs, which are kind of terrifying. The modern proofs are written in the language of cohomology, right? Group cohomology. And local class field theory also offers you a complete description of somehow a vast number of cohomology groups. Like you're interested in kind of H2 of gal K bar over K with coefficients in K bar star or something like this, the group cohomology. So class field theory tells you an awful lot about these things as well. But let me just tell you, so the final remark then, the final thing, local class field theories tells you, is a lot of statements about cohomology groups, but let me just briefly give you one of them. If L over K is finite in Galois, okay, so this is something we won't need at all, but I'm kind of rather hoping that I'm going to tell you enough to kind of cover you for class field theory for the rest of your life, and you might find that one day you'll need this statement. If L over K is finite in Galois, then if you think about it, then we've seen that WL so we have WL lives in WK, and this is finite index. I guess L over K is finite in Galois, so this is normal as well. This is a normal subgroup. And the quotient, of course, WK over WL is just canonically gal L over K. But class field theory is telling you the abelian. I'm interested in K, but class field theory, because it works for all K, it tells you something about L as well. It tells you about the abelianization of WL, right? So let's look at the commutator subgroup of WL. So the way this works is we've got WLC lives in WL. Remember, this is the closure of the commutator subgroup, right? That's the thing that we're going to quotient out by to get WL ab. And so therefore we can consider, so this is a characteristic subgroup, right? This is a characteristic subgroup. It's if I've got an arbitrary automorphism of WL, maybe not even an inner automorphism, an arbitrary group automorphism of WL, it will send WLC to itself, because WLC is defined in such a canonical way. So if WL is a normal subgroup of WK, and so if I take an element of WK, I can conjugate I can conjugate WL by this element. That sends WL to itself. It might not be inner, but it will be a random automorphism, so it will send WLC to itself as well. And so that means that WLC is actually a normal subgroup of WK. And we can take the quotient of this, right? So let's define WL over K to be the quotient equals WK modulo WLC. Okay, so that's not gal L over K. This is a huge thing because well, let's take WL over K apart, and I'll show you what we've just made. I'm giving the lecture on local class field theory that I really wish someone had given me when I was your age. That's what I've realized I'm doing. I'm telling you everything somehow in 1 hour, 15 minutes. I'm really attempting to tell you everything you will ever need to know about local class field theory. This WL over K is WK over WLC. And so therefore, we have the WL over K has some structure, right? This is the quotient of WK by WLC, but we have this WL, right? You see this, we have WK and then WL and then WLC. And this quotient here, WL over WLC, that's WL ab, and so we know what that is. You see, so WL over K, this contains L star, right? There, via RL. So we have an L star to WL over K, and now the quotient of this is WK over WL. You see we have a filtration, we have this filtration, WK, WL, WLC. So when I take the quotient of WK by WLC, there's this canonical sub, which is WL over WLC, which is WL ab, right? You see, so really this is WL ab. You see, but the point is by local class field theory, that's L star. So 1 to L star to WL over K, and now this goes to the quotient WK over WL, which is just gal L over K. Right, to 1. So we've got a canonical short exact sequence that looks like this. Okay, and now if you know some kind of yoga of group cohomology, so this extension then gives rise to an element of H2 gal L over K, L star. So gal L over K acts naturally on L star, and it turns out that this is the action here. So if you don't know what group cohomology is or anything, it doesn't really matter. It's just some formal. This is soft. There's just some way of unraveling. If you have 2 cocycles, then you get extensions like this. So what I'm saying is this local class field theory isomorphism gives us a very natural extension of this by this. So this is not a semi-direct product. This is a more complicated extension. So this is a non-trivial element of this H2. Okay, and this element's called alpha. It's called alpha L over K, right? And it turns out that H2, this group cohomology group, gal L over K, L star, is cyclic of order n. Of order n, which is the degree. And alpha is a canonical generator. So alpha L over K, which is just kind of dropped out the sky, is some random thing, and it turns out to be the most. When you start talking about class field theory in terms of cohomology, it turns out to be somehow the fundamental construction of the fundamental object, which is going to prove all the theorems for you. So alpha L over K is called somehow the fundamental class. And it's and basically you prove cut product with this fundamental class gives you some isomorphism between a wide range of cohomology groups. And of course, it's come out of the wash, but in practice, of course, what happens is that when you're proving the theorems of class field theory, you do lots of hard work to analyze groups like this, and you prove that this is cyclic and this has a canonical generator. And this all construction of this goes kind of hand in hand with the proofs of, so I haven't really constructed alpha L over K because I've constructed it assuming the existence of RK, but actually constructing RK and constructing alpha L over K all comes in one go. But this is just, if you just remember class field theory as this isomorphism, WK ab equals K star, then here's how you get this, this fundamental class, right? And now it turns out there's lots and lots of other facts about lots of, so I should just say, I won't now list any more facts about, there's a random fact that's sometimes useful. So, there's lots of, there are lots of cohomology groups that one can explicitly work out, that one can now compute using alpha L over K. In particular, kind of cup product with alpha L over K. Cup product with alpha L over K is some map between cohomology groups that in many cases is an isomorphism. So that's all I'm going to say about local class field theory, but for the vast majority of you, that might be all you'll ever need to know. So there's that. Maybe I should go forwards through my notes rather than backwards. Yeah, perhaps of the Wedelin group. Right, I think maybe I should probably say that, of course, so this says, as an upshot, we now understand the Galois group of the maximal abelian of the maximal abelian extension of K, right? So abelian. So what's an abelian extension? That means it's a Galois extension, and the Galois group's abelian. So let me just say L over K abelian. That means L over K is Galois, and the Galois group is abelian. Compositum of abelian extensions is abelian, right? Compositum of abelian extensions is abelian. And so therefore there's a maximal abelian extension so therefore maximal abelian extension K ab living in K bar, right? So we've got K bar, the picture I've been drawing consistently, I have K bar at the top and K at the bottom. But when I was doing low-level stuff, I would talk about now the maximal unramified extension and the maximal tamely ramified extension, which I could analyze rather explicitly. But here, I've got the maximal abelian extension, which is K ab. Okay, and to analyze this extension, I need local class field theory, right? So what's this Galois group here, right? Here, the Galois group is clearly Gal K bar over K, the abelianizations of this topological group. So the quotient by the closure of the commutator subgroup. Okay, and now, so what can I say about Gal K bar over K ab and the way it's going to work? You see, the point is that unramified extensions are abelian. You see, unramified extensions have got a Galois group that are related to the Galois group of the residue field, and those Galois groups are all cyclic, you see. So KNR lives in here, right? you see. So what we can do is we can do gal k ab over k, and that's going to surject onto gal knr over k, right? And that's z hat. And of course, there's a z here, right? There. And now, of course, and here we have whatever. We have the image of I. Well, I've got a name for it, haven't I? I've got I k ab over k. There, that lives in there. And we can put I k ab over k here. And now what's going on here? Well, of course, you can see we haven't changed anything here, and we've changed a z hat to a z. So we'll be unsurprised to find that I've got wk ab living in here, and that lives in there. And wk ab, we understand this is k star, and so to figure out what gal k ab over k is, we just have to kind of change the z to a z hat, right? So this is isomorphic to k star by local class fill theory by RK. And so this gal k, you see, this is kind of a good reason to introduce the Weil group, because now you can see this, this is the abelianization of the Galois group, right? You see this is gal, whatever. This is gal k ab over k is the abelian, this is the group we want to understand, gal k bar over k. We abelianize it, we get gal k ab over k. And gal k ab over k isn't quite k star. You can tell it's not k star because it's a profinite topological group. So it can't be k star because k star is not profinite. It's got OK star in which is profinite, but it's got this random z, you see. So you can see it's some kind of completion. You can see it's some kind of completion of this thing. I want to stop because I've said exactly the things I want to say, you see. And so therefore, so gal k ab over k, so gal k ab over k is then kind of non-canonically isomorphic to kind of OK star cross z hat, you see. And this is non-canonical because it involves choosing I've chosen some kind of a Frobenius to do this splitting. There. And this z hat is gal knr over k. There. And this is I k ab over k. And this group's abelian, and so you have a group with a cyclic quotient, then you can kind of non-canonically split it. But it involves choosing a uniformizer. So as an upshot, in this lecture I've told you without a proof, we're missing the proof, right? The existence of RK, I haven't told you how to do that. So this is gal k bar over k ab. So this morning we tried to analyze the inertia subgroup and the wild inertia subgroup, but today, this lecture, we somehow completely nailed the abelianization of this. And that was somehow, as I say, this was all known since the 1930s. So as a result, we knew the abelianization. And of course, we also know that this group, gal k bar over k, is what we're trying to understand. We also know it's solvable, right? Because there's a cyclic bit, and then a cyclic bit, and then a pro-p bit. So if we understand abelian extensions, and we also understand abelian extensions for all kind of, we understand finite, this gal k bar over k is somehow built from abelian groups in some funny way, and we kind of understand abelianizations, and so you would imagine that we could somehow put everything together and understand gal k bar over k completely with class field theory. But it's just too difficult because it's somehow, I've just sort of said, to understand solvable groups, all we have to do is understand cyclic groups, right? And in some sense that's true, but we also have to understand the glue, and the glue is complicated. It's a complicated non-abelian phenomenon. So somehow class field theory isn't enough to understand all of gal k bar over k. We understood the abelianization, and then for 50 years, we were stuck trying to figure out what to do next. So in the next lecture tomorrow, I'll tell you Langlands' amazing ideas, which explain how to understand gal k bar over k, which generalize this picture. I'm sorry that my first lecture I felt very uninspired. I was quite tired, but this lecture I'm kind of pleased with. This lecture, I don't know. I've said everything I want to say, and hopefully I've said it coherently. So I'm sorry about the first lecture this morning. But there you go.